Hi students. In the last class, I have given you the brief about what we have to see in heat effects, where sensible heat effects and latent heat effects. In today's lecture, we are going to see a few things about the latent heat. Okay, that means you are taking the system from state 1 to state 2. It could be evaporation process. Okay, if that is the case, or condensation process, any process that involves the phase change, there it comes the latent heat. So let us do some basics of the latent heat. So to do that, no, there are number of equations proposed. That means to let us know the calculations about the enthalpies associated with the latent heat of vaporizations or condensation process. If you remember the P and T diagram, so P and T diagram looks in this way. On the left hand side, it could be solid. On this in between the fusion curve and vaporization curve, it is called liquid. On this side, it is vapor. What we are interested in, we are not interested in any other phase change, because many of the chemical engineering process associated with the changes from the liquid state to vapor state, or vapor state to liquid phase. So in that cases, this vaporization curve is important. So on other side, it is called liquid, and on the bottom side, it is called the vapor. So anything that has brought from a liquid to the vapor state, and this curve detects the vaporization curve. And let us concentrate on the vaporization curve. What this curve is? This line is representing the combinations of temperatures and pressures. Okay, the combinations of temperatures and pressures where the latent heat of evaporation is happening. That means if you detect, at water, it will evaporate at 100 degrees centigrade at 1 atmosphere. That one point, it is representing the 100 degrees centigrade. The another point is representing the 1 atmosphere. So like that, if you change the temperature, that means if you keep certain substance in the liquid phase, and if you at its saturation pressure and temperature, and if you try to heat the things, suddenly it transforms to the vapor at the same temperature and pressure. This is called latent heat of vaporization process. During this latent heat, that means during the changes from the liquid state to vapor state, there is no change in the temperature or pressure that is going to see. So in such the combination of things at this liquid state to vapor state happens, the combination of pressure and temperature is termed as saturation pressure and saturation temperatures. So if you increase the pressure, the temperature is going to change. That means if you conduct the same vaporization process not at 2 atmosphere, maybe the boiling point is going to change. Okay, that means if you change the pressure, the temperature at which the vaporization process is going to happen, that is going to change. Okay, if you increase the pressure, the temperature at which the vaporization process also increases. If you decrease the pressure, the vaporization process, the temperature at which the vaporization process is also reduces. Example, if you take a water, okay, at what temperature water is going to boil? At 100 degrees centigrade, it can convert from the liquid state to vapor state. What happens if you maintain some vacuum inside this chamber? If you try to maintain the vacuum, that means if you reduce the pressure from 1 atmosphere to the lower than 1 atmosphere, then water starts to boil at low temperature itself. So that is what the combinations, the temperature and pressure combinations is going to set, right, the way at where the vaporization happens. If you change the temperature, at what pressure my vaporization is going to change. If you change the pressure, at what temperature my vaporization is going to change. So the point, this is the line that is going to say. Okay, that is because to detect the enthalpy of vaporization process, you should locate this particular line first. So based on this particular line, many equations proposed, right. One such an equation, latent heat of a pure substance. That means you are trying to see the changes of vaporizations of liquid or vapor, water, methanol, ethanol, whatever may be the thing you talk, a pure substance. So latent heat of a pure substance. That is that Clausius came up with this equation. If you wanted to find out the enthalpy change from liquid state to vapor state or vapor state to liquid state, you should know the following equation. You should know the temperature at which is going to happen. What is delta V LV? Delta V LV nothing but volume of the liquid minus volume of the vapor. Okay, what the delta V LV? Change in volume from the liquid state to vapor state. What is dP sat by dt? That is a slope of this particular line. This line is nothing but on the y-axis it is the pressure, on the x-axis it is temperature. The slope of the line is nothing but dP sat by dt. So if you know this particular informations, you can able to find out what is the enthalpy change, that is heat associated with the change in change in phase. Okay, then Clausius came up with the another equation. I mean, Clausius-Clapeyron came up with the another simplification, right? Delta, what is delta V is representing? Volume of the vapor minus volume of the liquid. He says that the volume of the vapor, that means in general gas occupies high volume than the liquid volume. So delta V is nothing but vapor volume minus liquid volume. Liquid volume, let us consider the neglect the liquid volume, and VV minus VL, vapor volume minus liquid volume is nothing but vapor volume. That means you can neglect the liquid volume. So simple delta VLV is nothing but volume of the vapor. And the another approximation he took, let us assume that this is an ideal gas. Okay, whatever the vapor that is going to form, this is an ideal gas. In such cases, we can use the ideal gas equation, PV equal to RT. So V equal to RT by P. Substitute, I mean, using this approximation, okay, the Clausius equation can be changed to Clausius-Clapeyron equation. So if you change this particular process, delta V LV, that means enthalpy of vaporization is equal to T into R into T by P. Okay, this will become, because this will become volume of the vapor. So you can take the derivative of dP sat by dt by assuming ideal gas law. So it will going to get delta H, that means change in enthalpy in the vaporization process, okay, is nothing but from T1 sat to T2 sat. Example, if you know, what is delta HLV and what is this Clausius-Clapeyron equation suggests that if you know the enthalpy of vaporization at one temperature and enthalpy of vaporization of another temperature, you can able to find out. So you can see delta H of liquid to volume. Delta H is vaporization, I mean enthalpy of vaporization. So it is nothing but T1 to T2, 1 by T sat square into dt sat. This equation will transforms to this particular equation, is equal to R into integral P1 sat to Pt, okay, into 1 by P sat into dP sat. Okay, if you integrate this, okay, 1 by x into dx, okay, you are going to get ln P2 sat by Pt. So you are going to get this particular equation. This is called enthalpy of the vaporization process, and ln P2 sat by P1 sat is equal to minus H into delta LV by R into 1 by T2 minus 1 by T1. What you are going to get this? You can measure this enthalpy of vaporization process provided the following things. One is, you should know what is P2 sat and P1 sat, what is T2 sat and T1 sat, what is P2 T2, what is P1 T1, one location. P1 T1 is the one location on this particular line, P2 T2 is another location on this particular line. That means if you know the two different points on this particular line, that means you can able to find out what is enthalpy of the vaporization process. So this is how the Clausius-Clapeyron equation you can use to find out the enthalpy of the vaporization process, provided if you know the two different points on this particular graph. So what is the use? And predicting the vapor pressures, this Clausius-Clapeyron equations, maybe there are many multiple uses. One such is predicting the vapor pressure. That means you can calculate P2 P1, T2 T1, provided if you know the other things. Calculate the latent heat, that means delta H you can able to find out. And there are inbuilt thermodynamic applications like phase transitions. That means if anything transferring from liquid phase to vapor phase or vapor phase to liquid phase, you can get some information. Those called determining the phase transitions. And the other thing is validating thermodynamic laws. There are some applications where this Clausius and Clausius-Clapeyron equation are used to validate some thermodynamic laws as well. So let us use some example let us use this Clausius-Clapeyron equation in some example. Given a pure component, saturated vapor pressure and temperature data at two different conditions are given. It is said that vapor pressure, okay, T1 at temperature T1 296 Kelvin and is 26264.5 Pascal. Okay, this is T1, and vapor pressure at temperature T2, that is 318 Kelvin. So this P2 sat is given. That means when the moment A said that it's a saturated vapor pressure data, then you can put the symbols T1 sat and T2 sat, P1 sat and P2 sat. So two different vapor temperature and pressure data are given. So using that, calculate the enthalpy of vaporization process. So simple, we use this particular equation. That means you have to calculate delta H LV provided P2 and P1 are given, T2 and T1 given, R is the universal gas constant value is provided. So in that case, as if you substitute the respective things in this particular equation and calculate enthalpy of vaporization process for a substance is given as 2922.543. I'm sorry, I have used maybe double dot. Just check for the calculation once. So delta H of vaporization process is joule per mole. Okay, this one way of getting the enthalpy of vaporization process is through this Clausius-Clapeyron equation. Okay, what if there is another method suggested by Troughton? Okay, it's more simplified version than Clausius-Clapeyron. It is said that you can able to find out enthalpy of vaporization at normal boiling point is by R into Tn is equal to 10. That means a thumb rule kind of a thing. That means you can able to get the enthalpy of vaporization at normal boiling point can be estimated. What is the normal boiling point? Normal boiling point is in general the pressure equal to 1 atmosphere. So example, water has a normal boiling point of 100 degrees centigrade. What is a normal boiling point? The temperature at which the pressure at 1 atmospheric pressure and what if you try to measure, that is a normal boiling point. So what is the normal boiling point of temperature of water? It is 100 degrees centigrade. At what pressure? 1 atmospheric pressure. That is what this N is denoting. Troughton's rule. Enthalpy of vaporization at normal boiling point divided by R into T normal Tn means normal boiling point of that particular substance will be always, the ratio is also always close to equal to 10. That is what this means is. So Tn is the absolute temperature of normal boiling point. R, okay, the R is given as 8.31 for joule per mole Kelvin. Example, water is a normal boiling point is 100 degrees centigrade at 1 atmospheric pressure. So according this particular formula, I can find out the enthalpy of vaporization of water is 10 times R into Tn. Tn, it is nothing but 100 degrees centigrade, that is 373.15 Kelvin. So R is equal to 8.31 for joule per mole Kelvin. Okay, if you do that, you get enthalpy of vaporization is 31.02 kilojoule per mole. So in reality, enthalpy of the vaporization at normal boiling point of is 40.6. Experimentally, the value is 40.66, but if you use the Troughton's rule and calculate the enthalpy of vaporization, it comes to about 31.023. This is what the difference between, because it is more and more thumb rule. So the thumb rule will not give you exact calculation, but it will give you a starting point at where to start. So that will help you in going for higher calculations. Okay, next is there is a Reidel, just like a Troughton. The Reidel also came up with another equation, that is trying to find out enthalpy of vaporization at normal boiling point by RT is given as 1.092 into ln PC. PC is the critical pressure minus 1.013 divided by 0.930 minus reduced normal boiling point. Okay, you can apply this particular formula to calculate enthalpy of vaporization suggested by Reidel. So PC, what is the critical pressure? Okay, that we are supposed to look into the data. Suppose if you are trying to find out the enthalpy of vaporization of water, so you have to take the critical pressure of the water. So what is TRN? Reduced temperature at normal boiling point. We are going to don't worry, we are going to see what is this. Water. If you look into the tables, appendix B, the critical pressure of water is 220.55 bar. You know what is the normal boiling point of water? 100 degrees centigrade. Okay, and what is TRN? Reduced normal boiling point. If you divide any temperature with its critical temperature, it will become a reduced temperature. So what is and you are trying to find out reduced temperature at the normal boiling point. So Tn by Tc will give you TRN. What is Tn? It is a normal boiling point of water. Example is 373.15 Kelvin. Critical temperature of the water is 647.1. So if you take the ratio, TRN is 0.576. So the information required for you to calculate the enthalpy of vaporization is provided. So delta Hn is estimated is 420.65 joule per mole. That is nothing but 42.045 kilojoule per mole. So if you compare with the, as per the Troughton, you got the value 31, the experimental value is 40. Now now you can see the value. Now according to the Reidel, okay, according to the Reidel you got 42, but experimentally it is 40. You can see it is more better approximation compared to the Troughton. The other the Watson came up with the other methods. Okay, that means if you know the enthalpy of vaporization at one temperature, you can find out the enthalpy vaporization at the another temperature. So you should know one condition in prior. That means at TR1 you should know delta H1. So delta H2 can be calculated at the another temperature. So the condition is, if we know the value at the condition 1, okay, condition 1, the other value at condition 2 can be estimated using the following relationship. So let us take that delta H, that means delta H of vaporization for water, that is, for example, you have take 2257 joule per gram. So here we have changed a bit units, don't worry about the units. Okay, enthalpy of vaporization for water at 100 degrees centigrade is given as 2257 joule per gram. So we have to find out enthalpy of vaporization of water at 100 degrees centigrade. So that means you already know the data at one particular condition. Only thing is you have to find out the enthalpy of vaporization of water at a 300 degrees centigrade. It is very simple. You have to apply this particular formula. First of all, you should know what is critical temperature. Critical temperature of water is something 647.1. TR1 is nothing but T1 by Tc. TR2 is equal to T2 by Tc. So T1 equal to 100 degrees centigrade, T2 equal to 300 degrees centigrade. Simply you substitute the respective variables, and finally the enthalpy of vaporization at a 300 degrees centigrade is nothing but 1371 joule per gram. So this is how this enthalpy calculations, because our if you remember, our agenda is to get some informations about the latent heat. So Reidel, Watson, and kind of Troughton's, Clausius-Clapeyron, these are the different kinds of equations from where you can able to get the data of enthalpy of vaporization. Why it is important? Somehow because all the things is we are trying to find out the changes in enthalpy. That means you are taking the system from state 1 to state 2. There might be heating process, there might be cooling process, there might be reaction process, there might be latent heat process. Sometimes combination, heating might also happen, cooling might heating might also happen, reaction might also happen, and latent heat also might have happened. So sometimes the combination of things will happen. In such cases, where to start and what kind of equations we are supposed to use, it will give you the glimpse of the things. I hope now you understood. Let us meet with the new lecture.